Welcome to Lecture 2 for Radiochemistry 702. This lecture is on chemical kinetics and thermodynamics, and it's in two parts. The readings for the lecture on thermodynamics and kinetics can be any general physical chemistry textbook that you're familiar with. One that I would recommend is More Physical Chemistry, chapters 4 through 7. The lecture topics are going to include thermodynamic laws, half-cell reaction, kinetics, acid-base reactions, and equilibrium calculations. Part 1 is going to focus on the first four. When you've completed Part 1, continue to Part 2, where the lecture will focus on equilibrium calculations. These lectures will provide a review of thermodynamic and kinetic concepts for applications to radiochemistry. Fundamentally, what we're going to explore is shown here. One is where we have an initial state and a final state. To traverse from that initial state to the final state requires some energy. And this activation energy, that's our thermodynamic consideration. Now, the time that it takes for this reaction to occur can vary based upon chemical conditions. So as this figure shows here, we have some products and reactants. Initially, we just have reactants. The reactants convert to products, and over time, an equilibrium is reached. The theme of these lectures is to discuss both these figures in terms of reactions that drive speciation, the chemical form for radionuclides, because understanding the chemical form of radionuclides is key to development of applications and understanding fundamental behavior. This lecture will begin with thermodynamic terms. One of the first thermodynamic terms we can discuss is heat capacity, which is, as you may already remember, the amount of heat required to raise 1 gram of substance 1 degree centigrade, or 1 degree Kelvin. For an example, aluminum metal has the heat capacity listed here of about 0.9 joules per gram Kelvin. Some of the data that we'll look at will be listed in calories, so here's a conversion factor between calories and joules. So you can use this equation, you can use this term to solve, for instance, what heat is needed to increase 40 grams of aluminum by 10 degrees, and that answer would be close to 360 joules. And over to the right, there is a figure that evaluates the heat capacity, the change heat capacity, for UO2 as a function of temperature. So that we can see that the heat capacity term can change as a function of temperature, and this implies that there are changes within the materials that are reflected by thermodynamic properties. Another definition that you may remember is exothermic. In other words, a reaction that produces heat at 25 degrees is defined as exothermic. An example is carbon plus oxygen going to CO2. The opposite of exothermic is endothermic, and those are reactions that require heat. Now, when we discuss some material or a system, we can talk about the energy content of the system in terms of enthalpy. This describes the energy of a system and really accounts for, as described here, energy transfer to the environment by heating, by expansion or heating. As an example, we have some enthalpy measurements listed here, H at T minus H at 298.15 K for UO2, and as we see from this, we see that enthalpy increases at higher temperatures. What's really measured is the change in enthalpy, delta H, and you can often determine that for a reaction by taking the products minus the reactants. Exothermic reactions are negative and they tend to be spontaneous. Enthalpy can also be estimated using bond energies. An example here is for ammonia. You can use the bond energy, so it's the products minus the reactants. So there are 3 nitrogen-hydrogen bonds per ammonia. There's 6 overall. Subtract that from the nitrogen and the 3 hydrogens. You get a bond energy listed here, and if you normalize that to 1 mole, you get something that's actually close to the relative to the actual value. So the bond energies, if you don't know a system, can actually be used to estimate the potential enthalpy. However, there's databases available that can be used to evaluate enthalpies. As an example, here's for the reaction of protons and CO3 2 minus going to CO2 in water. We see that we have the CO2 and water, so these are the reactants as listed up here. The products values are here, and if we take the difference, we can get the enthalpy of this system. Other ways of determining the enthalpy, if you wanted to talk about products at a from one temperature to another, we could actually look at looking at products from starting at one point as the reactants increase in temperature and then go back down. So if you don't have data directly go from one to another, you could use experimental data for a system that's closed and determine enthalpies throughout the products of the system. This would include both using enthalpy terms and heat capacity terms, as listed here. But overall, generally, your data is available. There's large databases available, and some examples are presented here for some pure substances and solution substances. Other terms similar to enthalpies, entropy, and actually combining entropy with enthalpy can give information on the Gibbs free energy of the system. Entropy is a randomness of the system. It tends to increase in delta S, tends to be spontaneous. Combination of enthalpy and entropy can be used in evaluating the free energy. The Gibbs free energy is defined here, where delta G, one term is delta H minus T delta S, or delta G equals RT log K. In this case, log K is the equilibrium constant with an activity at unity. Gibbs free energies are also available in databases. As an example here, a very simple reaction for the dissociation of water. What is the constant for the reaction? Well, you can use, if one calculates the Gibbs free energy, minus RT log K can be used to determine K, the equilibrium constant. So at 298.15 K, the Gibbs free energy of the reactant is listed here. This data is taken from databases. You get almost 80 kilojoules per mole. Log K, right, which would be delta G divided by minus RT, delta G minus RT is equal to negative 32.2. K is equal to 1 times 10 to the minus 14th. And this is basically kW, or the kW for water, which is 1 times 10 to the minus 14. For thermodynamic laws, there are 3 thermodynamic laws that can be utilized to understand reactions. One discusses, the first law is really focused on energy conservation. Energy can be changed or transferred, but it's a conserved term in any system. Second law of thermodynamics is that reactions tend towards equilibrium, that there's increases in entropy in a system. And the third law of thermodynamics actually is used to define absolute zero, where entropies of pure crystalline solids are zero at 0 K, or they tend towards zero as the temperature tends towards 0 K. For separations, particularly for the actinides, redox reactions are very important, so we should have a review of some fundamentals of electrochemistry and redox. So we should start with Faraday laws, where Faraday demonstrated that chemicals which react at electrodes are the quantity is directly proportional to the charge passed through the cell. A value for coulombs is the charge on 1 mole of electrons, defined as the Faraday. So 96,487 coulombs is the charge on 1 mole, and that's defined as the Faraday. This can be used as an example here, where copper 2 is electrolyzed by a current of 10 amps, and amps is a coulomb per second, for 1 hour between copper electrode. So how much copper reacts? Well, the reaction at the anode, copper goes to copper 2. At the cathode, copper 2 goes to copper. This is used for determining the number of the electrons. We have 2 electrons in the system. So 10 amps, that's 10 coulombs per second. It's 1 hour, so that's 3,600 seconds. And we know that the value for coulomb per mole is defined as a Faraday, so we get a value for how many Faradays there are. And we know that that's for moles of electron. We know that there's 2 moles needed for the copper reaction. So we use this to determine how many moles of copper react. Another important electrochemical reaction involves half-cell potentials. You can find lists of half-cell potentials listed in a number of places. Here's an example. There's a URL provided on this slide for finding some half-cell potentials. And they're defined from hydrogen gas to protons. At that point is defined as 0 volts. Other reactions are just compared to this hydrogen reaction. So, for instance, if we have a cell with zinc and an iron 3 to iron 2 couple at 1 mole, we can evaluate what will occur, what element will oxidize, what will reduce, and what will be the overall potential. If we look at the standard reduction potentials, we see that iron 3 to iron 2 is 0.77 volts, and zinc 2 to zinc is negative 0.76 volts. So the reduction potential for iron 3 is larger. This means that the iron 3 will be reduced and zinc will be oxidized in the reaction. So the balanced reaction will be 2 iron 3s plus zinc going to 2 iron 2s plus zinc 2. Now, even though we have to balance the moles in this reaction, the potentials are just added together. So 0.77 plus, because it's a negative, plus 0.76 volts is about 1.5 volt. The reason that we don't multiply the half-cell potentials is because those potentials it's defined for a mole of electrons. So the system's balanced as long as we're at a mole. Now, if we do have the standard potential, we can actually use that to evaluate the Gibbs free energy of a system through this equation, where the Gibbs free energy is equal to the potential, the negative of the potential, times the number of electrons times the Faraday constant. And again, if we find the Gibbs free energy, we can actually find the equilibrium constant from the equation that we discussed earlier. So as this example, copper plus zinc going to copper metal plus zinc ions, that potential is 1.1 volts. It's 2 electrons. So we can use this to evaluate the Gibbs free energy of the system. Knowing the Gibbs free energy, we can evaluate enthalpy, entropy, and complexation constants. Now, if one is not at unit activity, so not 1 molar, you could use the Nernst equation to determine the potential at the given conditions. So using the standard potential minus these terms R, T, N, F, and then your equilibrium conditions, you can use this to determine potential. So as an example, a given temperature, RT divided by F, this value is listed here. So what's the potential for an electrode of zinc and 0.01 molar divalent zinc? That's listed here. Here's the standard potential. We throw in that standard potential, plug this value into the equation, 0.0592, 2 electrons, log of 1 divided by 0.01, and we get a value of negative 0.82 volts. An important component in understanding reactions are chemical kinetics and chemical equilibrium, so kinetics and thermodynamics. They're important concepts in describing reactions. They identify you can use this to identify factors which evaluate the rates, for instance, temperature, pressure, reactants, mixing. One can use these understanding of these concepts to control reactions, often use them to explain why reactions fail to go to completion, and identify which conditions prevail at equilibrium. When we discuss equilibrium constants and thermodynamic data, this will be important for understanding which are the dominant chemical forms as one approaches equilibrium. Okay, the rate of the reaction can depend upon the conditions. As one is a general rule of thumb, for example, if one wants to double the reaction rate, the temperature can be increased by 10 degrees centigrade. However, the free energy, or the chemical thermodynamics, does not necessarily dictate the kinetics. Something can have very favorable thermodynamics, yet be kinetically hindered, so they can be decoupled. Thermodynamics is concerned with the differences between the initial and final state, where the kinetics talks about the rate of achieving that initial and final state. Kinetics are very difficult to evaluate from first principles, and some of the factors that affect kinetics are listed here. There are some general terms, though, that can be used to try to understand reactions. Ions tend to react rapidly. For instance, the formation of silver chloride from silver and chloride ions. These are very fast reactions. Those reactions that involve bond breaking tend to be slower. Redox reactions in solutions can be slow, particularly if there's bond breaking or bond making involved in these redox reactions. Structure can affect reactions, and a great example is with phosphorus. White phosphorus can be kinetically fast, but red phosphorus can be slower. Surface area, larger surface areas can enhance reactions. This is often used for development of catalysts. Something as simple as mixing is known to increase reaction rates. One way of describing the rates are rate laws. This is something that you should be familiar with and have seen before, where rate is equal to the factors of the components of the reaction, and that's called the rate order. The rate order is defined as the sum of the factors in the reaction, and understanding this rate order can help control the reaction. You can understand which properties have a large impact on the kinetics. And there are some simple evaluations one can make, where if you know initial concentrations at a time t, or a product concentration, you can evaluate equations that help define the rate order. And the equations are listed here with the order and the definition of K. One would plot some of the equations here. So it's something that's first order, log of the initial concentration minus log of the concentration at time t is equal to KT. Plotting this value against t should give a linear response with the slope equal to K. With rate law, there are certain things, as we've already discussed, that can increase rate law. Temperature. Catalysts are often used to increase rates of reactions. And this is something that one needs to be aware of, and we'll discuss later in class, where we talk about autocatalytic reactions. Particularly, this may influence actinide reactions, where redox plays a role. And if you have a system in which one metal ion is oxidizing and reducing as part of the reaction, increasing the temperature of the reaction, you can get an autocatalytic reaction in which the system can rapidly get out of control due to this temperature increase. One way of evaluating complexation kinetics can be through UV visible spectroscopy. Here's an example of some data with some ligands, and the complexation of uranium with these ligands is measured by UV visible spectroscopy. As a function of time, this absorbance band in this area is increasing. On the left, this is the full UV visible data. On the right is the absorbance sun from 250 to 325 nanometers for this ligand with uranyl at pH 4. We see that there's an increase. We can use this to describe the increase, where basically the absorbance total between two wavelengths is equal to some initial amount plus some addition of the absorbance or some change towards equilibrium, and we're plotting this with a first order decay constant, a first order constant. This is very similar to radioactive decay also being first order. This was evaluated where the absorbance initial, this delta absorbance that's due to the equilibrium, we've got the equilibrium constant, so you can determine how much time is needed to reach a certain percentage of equilibrium through this term. And one of the consequences of this study was showing that the ligand did bind uranium, but at a pretty slow rate, so it may not be the best ligand for doing extractions. Another form of equilibrium reactions are acid-base reactions. One can describe much chemical interactions as a reaction between acids and bases, or an acid is just defined as something that donates a proton and a base accepts that proton. There's a number of reactions that are listed here. What I want to point out is that some compounds can act as both acids or bases depending upon the reactions that they're involved with. And there are certain strengths that acids or bases have, and this is listed here on the right side, where we have conjugate acid, conjugate base. For instance, perchloric acid, HClO4, it's a very strong acid. It deprotonates while the conjugate base, perchlorate, is a very weak anion for interaction. We often use perchlorates as an ionic media that does not interact with metal ions. And as we go down, the acids get weaker, but the conjugate bases get stronger. For a number of acids, we can talk about dissociation constants. So if we have a general acid HA plus water, it can go to the deprotonated acid plus hydronium or the proton. A general equation, an equilibrium equation, is the products divided by the reactants, which are listed here. For acid, we can have a term that Ka, and this is the deprotonated conjugate base plus the proton divided by the bound acid. The pKa is equal to minus the log of the Ka. This is a term that's often used to evaluate acids, because as we'll show, the pKa is a very good handle for understanding what pH is necessary for deprotonating that acid, and conversely, it gives you a very good idea of what pH that acid can buffer. And here's an example of some acids with the formula for the acid and the Ka. There's databases for all these acids. One can use this as a calculation to determine a pKa. For example, a liter of 0.1 molar acetic acid has a pH that's listed here of 2.87. What's the pKa for the acetic acid? Well, the acetic acid, here's the protonated acetic acid plus water goes to the deprotonated plus the acid. If I look at this equation, I know that the amount of deprotonated plus is equal to the amount of the acid. Both of these are equal to the pH, which is 2.87. I can use my general equation for the Ka, which is equal to the deprotonated anion plus the proton divided by the acid. 10 to the minus 2 times 2.87, that's doubling of the 10 to the minus 2.8, divided by 1 minus 10 to the minus 2.8, because that's the amount of the acid that became deprotonated. That's equal to 1.84 times 10 to the minus 5, and that's actually equal to the pKa of 4.7, and acetic acid has that pKa. These weak bases in acids, such as acetic acids, can be used as buffers. And what's useful about this system, if you have an experiment in which you want to try to maintain a given pH, a buffer can often be useful. And basically, it allows the weak acid to either absorb protons or provide protons to maintain a pH within a given range. If an acid is added, to this example with acetic acid and the sodium acetate, hydronium reacts with the acetate atom, forming the undissociated acetic acid. And if base is added, the hydroxide reacts with the hydronium ion, forming acetic acid, and this acetic acid dissociates. Okay, so buffers can be made over a large pH range and can be useful in controlling reactions. And as we discussed, one of the useful terms is the pKa, and what the pKa is generated from is if I rearrange the Ka, where Ka is equal to the deprotonated acid plus the proton concentration divided by the protonated acid, I rearrange that equation where fundamentally the hydronium and the proton is equal to the Ka times Ha divided by A minus. Well, I write this as pH. That's pH is equal to pKa minus log of the concentration of the Ha divided by the A minus. Now, a buffer is best when the deprotonated and protonated concentrations are the same, so it has the largest capacity. So if these are the same, this will be equal to 1. The pH would be equal to the pKa minus log 1. Log 1 is 0. Basically, the pKa is very useful for defining a buffer range, where a buffer is suitable for you can buffer within a suitable pKa region by plus or minus 1. So when we talked about acetate with a pKa of 4.8, that can buffer from about 4 to 5 pretty effectively. The last constant that we will discuss in this lecture is the hydrolysis constant. It's a very important reaction because it's fundamentally the reaction that metal ions have with water. If one looks at water, water can dissociate into proton and hydroxide. This hydroxide is available for reactions, and from the Kw, the concentration of the proton times the concentration of the hydroxide is equal to approximately 10 to the minus 14th at 25 degrees. These metal ions, depending upon metal ions, they can form hydroxide products with water. In this example here, the reaction is balanced. These constants are listed for many metal ions with different hydroxide amounts, so mono, di, trihydroxide, and an example of the database is provided here. What's important about these hydrolysis constants, and we'll get to this in the next lecture, they vary according to some of the properties of the metal ion, particularly the charge on that metal ion. Metal ions like tetravalents, so +4 metal ions, readily hydrolyze. Trivalents, hexavalents, a little bit less. And then things like pentavalents, monovalents, very little hydrolysis. In part 1 of the lecture on thermodynamics and kinetics, we reviewed thermodynamic laws, half-cell reactions, kinetics, and acid-base reactions. When you've completed this lecture, please continue to part 2, where the discussion will focus on equilibrium calculations.